All right, so we are looking at, or finally entering, the second semester of calculus. So we are going to essentially be learning how to do derivatives in reverse. So calculus is broken up into two parts. You have the part where it is deriving, and then the part called integration. So what we're going to do today is introduce integration through area under a curve known as a Riemann sum. So Riemann sums came or got their name from German mathematician Riemann. He did his most famous work in non-Euclidean geometry. So we'll kind of look at some of that when you get into Calc 3. He did differential equations, which you guys should know are those dy dx equations, and then number theory. So differentials come into play with area under a curve as well. And he apparently worked with Einstein's theory of relativity as well. So in example 1, it says that suppose we're driving on a road trip. And once we get on the road, we're on the highway. The highway's long and boring. We're taking the PA Turnpike, right? We're heading to Philly. So once you're on the Turnpike heading to Philly, you turn on your cruise control and you're just driving. It's flat, it's straight, you're avoiding the trucks, etc. So suppose that from hours 2 to 4, you have your cruise control set to exactly 70 miles per hour. How far do you travel in those 2 hours? So if you think about your pathway, I don't know what I'm doing before I get to cruise control, but I know that at hour 2, I turn on my cruise control to 70. My cruise control is going to remain at 70 until hour 4. So going back and just doing math the way you know how to do math, you would say, okay, 2 hours, 70 miles per hour, means I drove 140 miles. I started doing example 2. So it says sketch a graph modeling the situation in the above example. Geometrically, how could you indicate the total distance traveled? So if this graph right here represents my traveling time, that would geometrically be represented by a rectangle, where the area of that rectangle would represent my total driving distance. So area would equal the base times the height. Well, the base is going to be 4 minus 2. My height is always 70. So once again, giving me 140. So it's really nice to find distance traveled using area of a curve when that curve is a constant, because that constant will create a perfect rectangle. What happens if velocity is not constant, which is many of the cases? So say for instance that we have a velocity function in miles per hour, it's given by 10t minus t squared, where t is in hours. And we wanted to know the total distance traveled during the first 10 hours. So we know at time 0, distance traveled is 0. We would want to know where we are at 10 hours. So 10 times 10 is 100 minus 100 squared. So at 10, we've reached our destination and are stopped again. That means that the maximum of my destination, or the farthest I've traveled in what direction, is going to happen at hour 5. So 10 times 5 is 50. 50 minus 5 squared is 50 minus 25. And then we have your other quadratic forms. So, looking at this, that's not a perfect rectangle now. I can't find the area under the quadratic. Well, I could find the area under the quadratic using a rectangle. But if I were to do that, I would probably end up with a whole lot of what? Blank, unaccounted for area. Because that rectangle is no good. And then even if I tried to do a rectangle this way, so if you were to do this, I would do this if I had to, like maybe a rectangle and semicircle, or maybe triangle. I think a triangle is probably the best. So again, it says geometrically speaking, do you think we can find the total distance traveled in the same way as before? We definitely can't find it in the same way as before, because the before total distance traveled was perfect. This time, if I use that triangle, my total distance traveled will be a approximation, but a pretty good one. So the area of the triangle would be 1/2. The base is 10. And then the height, or the altitude, has to form a 90-degree angle with the base. And the height is going to occur at hour 5, but the height is the y value, so 25. So in calculus, that's our estimate. You can find the actual, what I hinted at, or I talked about on Wednesday, using something called an integral. And you would integrate the function from 0 to 10, so your bounds of the base, and then you'd integrate your curve. And just to give you an idea of how good our estimate was, not very good, but your actual is 166.66. So again, that 166, that's different. That error is this space. So if I had asked you to look at that graph we had in that space, we would have predicted our approximation to be an underestimate, because the geometric shape I created was always under the actual curve. So that's why our prediction is an underestimate, because our shape is always under the actual curve. So the key to finding total distance traveled in that last example is a method similar to the first example. What could I have done to make my estimate better? I could have made more shapes. I could have made more triangles or more rectangles that would have been closer to the heights of the actual curve. So what we're going to talk about today is something called a Riemann sum, where we are going to create more than one triangle to approximate the area under a curve. So curves are curved, triangles are flat. So our approximations are never going to be exact, but we're going to spend a quality amount of time getting them as close to exact as possible. So our goal for today is to figure out a way to find the area under the curve. And today we're going to talk about LRAM, RRAM, and NRAM. We'll introduce the trapezoid rule later. Technically our textbook has trap rule in like the end of chapter 5, but I bring it into the chapter here because it fits way more nicely. So it says using the left endpoints, we want to determine the area between x squared plus 1 and 0, 2. So our goal is to approximate the area of the green shaded region to the best of our ability. And now we're using left RAM. So we're going to find or determine the area using L RAM. And we're going to use, and I believe your paper has it in there in its directions, we're going to use 4 rectangles. So the width of a rectangle is determined using a formula called delta x equals b minus a over n. So that is the width of our subintervals. We figure out or determine each width by taking A and B from the interval length, subtracting them, and then dividing by the number of rectangles we're informed to use. So in this case, we are informed to use 4 rectangles. So that means the width of every rectangle I'm going to create is 1/2. So if I'm using the left endpoints, I'm going to need the height of each rectangle every 1/2 of my function. So starting at 0, we're going to go in increments of 1/2 in my table, because those are going to give me the left endpoints. So when x is 0, f of x is 1. Because I plug 0 in to my curve. When x is 1/2, f of x is 1/2 squared, so a fourth plus 1. Unlike you guys, I like fractions, so I'm gonna go with 5/4, not only 0.25. Okay? F of 1 is 1 squared. Well, 1 squared is 1. 1 plus 1 is... and 1.5 squared. So again, 1.5 is really like 3/2. So 3/2 squared is 9/4. 9/4 plus 4/4. It's 13/4. And here's why I like my fractions. So like my 9/4 and my 13/4 and my 5/4 can like add together. Okay. So left ramp is creating left rectangles so all of my rectangles are being created at the half height. So this is the base. The height comes from the left side. So rectangle, 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 where the height comes from the left side and the width or the base comes from the delta x. So the area of this first rectangle is 1/2 times 1. My second area is 1/2 times 5/4. Yep. And then 1/2 times 2. And 1/2 times 13. When all of the widths of your rectangles are the same, you can multiply each height by 1/2, or you can say that the left ramp is equal to the base factored out. You can sum all of your heights and then multiply by half. Because now to get the total heights, I would add them all together as these fractions. Or what you could do is add all of the heights and then multiply by a half. Both are going to work. So 1 plus 2 is 3, 5, and 13 gives you 18/4. So 3 in terms of fourths, you would have to multiply by 4/4 and get 12/4. So 12/4 plus 18/4 gives you 30/4. Or 15/4 or 3.75. So all of these areas add up to 3.75. And if you added these together, again, 13 and 5 gave you 18/8, and then add in your 1 and your 1/2. So that's 8/8 plus 4x plus 18x. And you would have seen once again, 18 for 8 gave you 38, which also gave you 15. So you can do either method. You can find each individual rectangle's area and then sum your rectangles, or you can find each height, sum them, and then multiply by a half. The only time you can choose which of those two methods is if each rectangle's base is the same. So again, all of our rectangles had a base width of 1/2. There will be times where we might have a table of values and our base widths aren't the same, therefore this method doesn't work the same. Now you have one sheet of paper. I'm going to cheat and steal my table for my next page. So go ahead and look at the next problem, and our next problem says that we are going to do the same thing, but now we're going to use a method called right endpoints, or RAM. So I stole my table from my page before because once you found some of the endpoints, if your delta x doesn't change, your endpoint heights don't change. So now we're using right endpoints, which means instead of starting on the left side of the curve, we're going to start with the points on the right side of the curve. But what happens is these middle points didn't change, right? So the 1/2, the 1, and the 1.5 from my previous table get used again. So I still need them. The piece I don't have from before that I need this time is 2. So the height of the rectangle at 2 is 2 squared, which is 4. 4 plus 1 is 5. So looking at the fact that this time I'm going to be using these values, and last time I didn't use the 5, but I used the 1, do I expect my RMs to be sum to be greater or less than the previous sum? Greater, right? Because we're using a value that is bigger. And if you go back and you look at my drawing, was my left RAM an over or an under approximation of the real one? Because all my rectangles are under exactly. So this was an under approximation of the actual because all of my values are below my curve. So that's an underestimate. And this time, when I draw in all of my curves, all of my rectangles this time are above by like a fair triangular amount. So I would predict my right endpoint, or my RAM, to be an overestimate. So RAM equals 1/2, because the base of every rectangle is the same, times the sum of all their heights to get each area. So again, I'm looking for all 4 areas. So I'm going to add all 4 of their heights all of the rights this time come from the right side. So that first right rectangle has a height of 5. This rectangle here has a height of 13/4. My next rectangle has a height of 2. And my last rectangle has a height of 5/4. The order you write them doesn't matter. I just, for purposes of helping you remember, I usually write the left endpoints starting with the left for the lowest value. And for the right endpoints, I usually start on the right side and go down. So that way you see the difference in where you're starting. So 5 plus 2 is 7. 7 plus 18/4 is like 28/4 plus 18/4. So 28 and 18 is 38. 38 plus 6 is 36. 36 divided by 4 is 9. 9 divided by 2. I said 36 divided by 4 instead of 46 divided by 4. So wait, so now you have 1/2 times 46 divided by 4, which is half of 46 is 23, so you have 23/4. So about 5.75. So again, you can see that this value is bigger than the previous one. The last one was like 3.75-ish. This one's 5.75-ish. So, over. And then we have MRAM. MRAM is the midpoints. So the midpoints are probably the biggest pain because these ones aren't usually the numbers you're repeating. So if you had those same 4 rectangles, MRAM doesn't come from either endpoints we already know. The MRAMs come from the midpoints of all of these. So you would have to find the height at 0.25 and make your rectangle. At 0.75 and make your rectangle. At 1.25 and at 1.75. So I already did them on my calculator for time sparing purposes and mathematically. I don't want to do 0.25 squared. Like, that's 1/8. So MRAM is the same 1/2 because the distance of each rectangle didn't change. All that changed is I'm not using an endpoint, I'm using the midpoints of all of the endpoints. So you have to know, like 0 plus 1/2 is half, 1/2 divided by 2 is 1/4. So like these are all the midpoints using midpoint formula. So midpoint formula is like x1, x2 divided by 2. So if you forgot how to find your midpoints, again, you can see them if you know, kind of mathematically, but this is how you get the midpoints. So then it's 1.0625 plus 1.5625 plus 2.5625 plus 4.0625. So those are all the heights of the midpoints. You would add all of those together, divide that number by 2, and 4.6245 is kind of in the middle of that 5.75 and 3.75, right? So if you think about all of your LRAMs and RRAMs, MRAM in this case is probably the best approximation to the actual because it has the least amount of space above and under. They kind of like match each other. So remember, to find the width or base, you do B minus A over N. I have it at the top for you. You can also write it down at the bottom. That's the most important piece. That's what we call delta X. If you think back to differentials, we said that delta X was kind of like a fancy way of saying dx. So we ended chapter 4 with differentials, where you had dx on the right side, because we're going to pick up chapter 5 with that same idea of dx. This is what I added to my slide and got deleted. So it says a particle moves along a straight path. The graph of the particle is given below. That's the equation for the particle. It says what's the total distance from 0 to 2? We're going to investigate the total distance from 0 to 2 using Riemann sums. So the first one says use a left Riemann sum with one subinterval to approximate the area between the curve and the x-axis. So if you're using one subinterval, n equals 1, my interval is 0 to 2, so that's my a to b. So my delta x is 2 minus 0 over 1, where the width of my rectangle is 2. So if I'm using a left Riemann sum, I need the height of that rectangle on the left side. Is that going to be a very good approximation? No. So what is that LRAM or LRAM approximation? Well, it's height of the rectangle times the base of the rectangle, which is 2. This is an extreme under approximation. What happens if I say instead of one subinterval, I want to use 2 subintervals? So now, left Riemann sum, but I have 2 rectangles. So my delta x would change to 1. Now my area is 1. The first one has a height of 1. The second one has a height of 1.5. Because you plug 1 into that function and you get 1.5. So now I get the area as 2.5, so it's bigger, but is that a good approximation yet? Not really. What happens if instead of LRAM I say, all right, well let's try it from the right side. Maybe since the curve is concave up, the right endpoints will be better. I get 4.5. Now what's wrong with my 4.5? It's an over approximation. So what could we do, or what do you think would happen if instead of 2 subintervals, we had more subintervals? Would my approximation be better or worse? Better. So the greater your n, so as we increase the number of subintervals, my approximations would get better. So increase and better approximations. And then looking at these, or the previous graphs above, which Riemann sum was an overestimate, and which Riemann sum was an underestimate. So all of our right endpoints were above our curve because our curve was concave up and we came from the right. So the right Riemann sums were an over. And the left Riemann sums were an under. That is your first introduction to integration. Integration is area under a curve. All right, let me get